Right, so this elastic collisions question is all about this diagram, uh, and we've got a small ball being projected towards two walls, lots of information in the question, and we're trying to show what the final velocity is in terms of vectors. Right, I'm just going to look at this case. I'm going to look at it a slightly different way, which is the way most of you probably learnt from the book and in your class. So what's going to happen is we're going to start off here, we're going to collide with wall AB, then with BC. So let's look at the first collision. Okay. Now it does tell you in the question the direction of the walls. So this one's relatively easy because what we've got is the wall A to B is in the I direction, so it comes in with velocity 2I minus 3j, and so then it's going to bounce away. Now what we know is parallel to the wall there will be no change in the velocity in that direction, so we can just fill that bit in straight away. So that's going to be 2I, and then if I just call this WJ for now, let's find out what that is. So as this wall's in the I direction, the J direction is that way, so that's perpendicular to the wall. So if I look at perpendicular to the wall, this is where we can use Newton's law of restitution. So the coefficient of restitution between wall AB and this ball is a half. So a half is going to be our speed of separation over our speed of approach. So our W is 3/2. So after the first collision, we now are moving with velocity 2I plus 3/2j. And I've got you 3 marks in the mark scheme for that bit. And then we're going to need to look at the second collision. Okay, so if you've been working through questions in the book, you've probably been doing things like this with angles rather than completely with vectors. So let's have a look at how we could do this using angles. So now we want to do the collision with BC, and we want to know some angles. I'm just going to label the angles in this triangle. So if I look at my diagram, I can work out what alpha is by using our velocity that we have after colliding with wall AB. So we could draw a little triangle with alpha. We know that's 2. We know that side's 3/2. So we know tan alpha is 3/4. Now in the question, it tells us the direction of BC. So we could use the direction of BC to work out beta here. So BC has direction -I plus 3j. So -I makes that side 1, 3j that side 3. So tan beta is going to be 3. And so the angle our current velocity is going to make with the wall is theta. So theta is obviously looking at a triangle. It's 180 degrees. Take away alpha, take away beta. So that makes that, if you use all the angles we found so far, approximately 71.565 so on degrees. And you can work out that tan theta is 3. Once we know tan theta is 3, your calculator is actually accurate enough to do that, or you could work it out for some triangles and some trig. But once you know tan theta is 3, we can also get that sine theta is 3/√10, and cos theta is 1/√10. That's quite easy to do using a right angled triangle. What else do we know about our velocity here. So if I call this velocity, the velocity we've got after the collision with AB, W now, then I can work out that our magnitude of W is 5/2. So now I know what my velocity is before I hit BC. Right, so now we're carrying on looking at the collision with BC using these facts. Right, so here's our wall, BC. We're coming in here with our velocity. And once again, so parallel to BC, there's going to be no change in velocity. So parallel to BC, our initial velocity parallel is going to be 5/2, so the magnitude, cos of theta, and we called that theta. Okay, so that's 5/2 times 1/√10, which is √10/4. Okay, perpendicular to BC. Right, we can use Newton's law of restitution again. So this time our coefficient of restitution is 1/3. So 1/3 is going to be our velocity perpendicular to the wall after hitting it. So our speed of separation divided by our speed of approach, which is going to be 5/2 sine theta. So we can get the velocity perpendicular afterwards is going to be 1/3 times 5/2 times our sine theta, which is going to be √10/4. Oh, obviously, parallel to the wall, there's no change in velocity, so our approach and our separation are going to be the same. Right, so now we've got that our ball comes away from the wall. So after the collision, with BC, we've now got that we are moving off. There we go. We're moving away from the wall. Now, parallel to the wall, we've got velocity √10/4, and perpendicular, it's also √10/4. So that means our angle with the wall must be 45 degrees now. We can work out our magnitude afterwards. So I'm just going to do √10/4 squared. So the magnitude of velocity after we close the wall is now √5/2. We've got to turn this back into vectors, okay? And we've got to deal with the fact that the wall BC was at an angle, and we're moving at an angle to the wall. So if you remember in our original diagram, I called that angle beta. And if we go back, so in our original diagram, and you could work out using direction of the wall that tan beta was 3. So there's our angle beta. Okay. And now we're moving away from the wall, and our angle relative to the wall is 45 degrees. And what I actually want to know is in terms of vectors, so the I and J direction. So the I direction is parallel to the baseline, which was AB there, and the J direction is perpendicular to that. So I want this angle in here. So if that angle is beta, then this angle there must be beta minus 45 degrees. So if I'm going to turn this back now into vectors, then my velocity if you look at the direction as well, so a little bit of common sense here, we're now moving in the negative I direction, so that must be negative magnitude of my velocity cos, so I'm looking at this side here using this angle, so that's the adjacent side, and that angle was beta minus 45 degrees times I, and I'm moving in the positive j direction, so it's going to be root 5 over 2 sine of that angle. And then if you work all that out, you'll find that it's negative I plus a half j, which is what you were required to find. Now, one thing with this question is it is a show that. So whatever possible, it's good to work with exact figures. I'm not sure, we didn't have a mark scheme for this version, as this is just sample assessment material and I hadn't considered people answering it this way. So that's why I made sure when I was dealing with the angles, I wrote down the exact values rather than writing sine 71.56, etc., because that's not an exact value. So whatever possible, if it's to show that question, keep your values exact.